Welcome back, everyone. Today we will continue with our principles of featureization and dive a little bit deeper into how we are actually going to do the featureization. So far we have looked at composition-based feature vectors, and slowly now we are starting to move towards the structure-based feature vectors. Now the composition-based feature vectors were the low-hanging fruit. Those are the ones which are easy to describe. As we move towards a structure-based feature vector, what we are first going to do is we will talk about representation of crystal structures and molecules. So representation of crystal structures, for that we have already discussed a little bit about the graph neural networks and the sparse graph neural networks, or the sparse GNNs. For the molecules, especially for those of you in the area of material science who may have more interest looking at organic molecules like polymers and so on, it is important that we look at a slightly different way of featureization, and this is where the concept of molecular fingerprints comes into the picture. So the focus of our today's discussion is going to be on molecular fingerprints. Now, molecular fingerprints, they will work in a way which is fairly similar to how you do forensics, that you have got the fingerprints for humans, which are unique signatures of whom it belongs to. So that is the idea, that you come up with some way of finding unique features which are unique to different types of chemical molecules. And so those are the ones that we are going to call the fingerprints. And once we identify the fingerprints, we will be able to simply go ahead and identify those type of molecules. So once those molecules are identified and once those molecules are well defined in the form of some sort of a feature vector, one can then include them into the data set that you have constructed in addition to the input features as well as the output features, and then use this feature vector that we created from the fingerprints in order to do our machine learning. So the key part over here is simply to create the fingerprints. Once that is done, we are on our way, and we can then start using any of the standard machine learning models. Now, as we get started, I should mention that this concept of molecular fingerprints are actually fairly well developed because the genesis of this type of work comes from the area of bioinformatics. And in bioinformatics, people have been applying machine learning even longer than people have been doing that in case of metallurgy and so on. So we are going to borrow the concepts from bioinformatics as we start getting into this idea of molecular fingerprints. Now, just before we get into the molecular fingerprints themselves, let us just do a little bit quick recap of what we had discussed in the last lecture, because that will provide a very natural segue to our current lecture. So last time we were looking at composition-based feature vectors for most part, and we were trying to predict the phase selection in case of high entropy alloys. And by phase, we were talking about different crystal structures like phase-centered cubic, body-centered cubic, or a different type of crystal class called the intermetallics. And there we did a little bit of one-hot encoding type of work, and what we did was we created a feature vector where the presence or absence is given by 0 or 1. Now this is going to be exactly same idea that will now transfer over to the case of molecular fingerprints. If certain parts of a molecule are present, certain structures are present, for example, we will use 1. If some certain structures are absent, we will use 0. So I just mentioned this so that you can recap the previous lecture if needed, and you can get an idea of what we mean by this type of feature vectors with a combination of one-hot encoding. So the key concept for molecular fingerprints is related to this only, that feature vectors can be created, and these feature vectors can be set up to count the presence or absence of different chemical entities in a chain, or you could count the number of entities and the relative distances between the entities. So this idea of finding the relative distances between the different entities and how many times the same relative distance occurs is something which will help us determine whether the two chemical molecules that we are going to compare are similar or not. But otherwise, what you can see, that when we talk about molecular fingerprints, it's the same idea, but it's a little bit more versatile, because not only are there methods by which we can count the presence or absence of chemical entities, We can also count the number of entities and the separation between the entities. So this is where the molecular fingerprint concept is going to be a little bit more sophisticated from the fairly simple-minded concept that we discussed last time. Now, this type of fingerprinting technique has got a lot of applications. So if you look at drug discovery and design, so basically our pharma industry, where bioinformatics becomes quite critical, that is a place where this type of molecular fingerprints are used quite extensively. Of course, nowadays we are extending these concepts to material science. So for those of you who are interested in working with polymers, you will again find that this type of fingerprinting methods are extremely useful for you. Now, I had mentioned that this area of bioinformatics is a little bit better developed than applications of machine learning and material science. And so what you will notice is there are a number of packages which are already available in the literature. Number of them can be used even free of cost. So I'll just mention those packages in case any of you would want to get into this molecular fingerprinting in greater details. So some packages are Scikit Fingerprints, RDKit, CDK, OpenBabel, and so on. RDKit is one which is really popular, and Scikit Fingerprints is really a good place in which you can get started, especially because scikit-learn would be a very easy and gentle Python package with which you can get started with machine learning. Now, of course, there are other packages that one can do for machine learning. You've got TensorFlow, Keras, and so on and so forth. But scikit-learn is a fairly easy package. And then based on that, you also have this Scikit Fingerprints package. Otherwise, if you really want to get into this in a little bit more detail, I would strongly recommend that you look up something like RDKit, which is a fairly comprehensive package incorporating molecular fingerprints. Now, there are a number of fingerprint schemes as well. So you have got things like smiles, deep smiles, and selfies. So in this lecture, we'll basically talk about a couple of the methods, smiles and selfies. Smiles is a relatively older method. It was improved upon a little bit and modified a little bit in order to come up with the deep smiles. And then there was another package called selfies, which has come up recently, which can actually sort of mask over all of the number of the deficiency of this smiles scheme of molecular fingerprinting. Selfies is just the new advanced scheme. So let us go over what these schemes actually are. We will start with the SMILES scheme. So SMILES is an acronym. It stands for Simplified Molecular Input Line Entry System. And this is basically a text-based notation, and this encodes the positions of atoms, which types of atoms are there, bonds, branching, and so on. So for example, if you were to use a SMILES scheme, ethanol would be written as CCO, and benzene would be written as C1, 5 C's, one after another, and then 1. So we will actually look into how this nomenclature is coming about with these examples of ethanol and benzene. But just a few things to keep in mind. You can see that in case of ethanol, I've used C as uppercase. In case of benzene, I've used C as a lowercase. So the lowercase letters are often used for denoting whenever you have got the aromatic ring. So benzene is a molecule which has got an aromatic ring, and therefore in case of benzene, I'm using lowercase. Whereas if you look at something like ethanol, it does not have an aromatic ring, and therefore I'm using uppercase. So whenever you see this type of SMILES nomenclature and you see a uppercase, it means you do not have an aromatic ring. If you see a lowercase, it means that you've got an aromatic ring. Then after that, you've got some digits. So for example, in case of benzene, you have got a couple of ones. Now these digits simply denote where this aromatic ring is starting and where it is closing. So one can say that it is starting at the beginning of the first carbon, and then after the last carbon, the ring is closed. So basically what you are doing, this 1 is being inserted after the letter that denotes the position of the start of the ring and the closure of the ring. So this is a type of nomenclature which is very widely supported in a lot of the cheminformatics packages that I just mentioned earlier. So things like RDKit and all, they all support this type of SMILES encoding of the molecules. So let us look into understanding the nomenclature of how SMILES work a little bit more clearly. So we are going to take the examples of two molecules. The first one is C2H5OH or ethanol. And so in case of ethanol, basically we can write this thing as CH3, CH2 and OH. Now when we are using smiles, what we are basically going to do, we are going to simply look at this carbon atoms and the oxygen atoms, and whenever something is not mentioned, in order to fulfill all the bonds, the rest are going to be hydrogen. So what we do in order to represent a molecule like this, for this first carbon atom we write a C, for the second carbon atom we write a C, and then after that you've got a hydroxyl group, so you write O for the hydroxyl group, and therefore ethanol is represented as CCO. Now if you look at something like benzene, the benzene molecule looks like this. So in case of benzene, I have to start numbering everything. So I have my first carbon over here, the second, the third, the fourth, the fifth and the sixth, right? So therefore I start representing it. Remember that I have got an aromatic ring over here, and therefore I will be using small letters. So I start with a small c. Now my aromatic ring actually is distributed over all of this, right? And therefore I say that the position of the ring starts at 1, and then I will put all of the other carbons in there, and after I have written the last carbon atom, I am simply going to close the ring, and so I write 1 over here, and therefore ethanol is represented as C1, C, 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 1. So this is basically how the SMILES system is used to encode the information regarding the molecules. Now, one of the advantages of the SMILES based system is that this type of text based representation of the molecule can be one hot encoded as well. So what do I mean by it? So here basically what I will say is, so I can create a feature vector type of table, and so when I create a feature vector type of table, I have to put things which look like this. So basically I have the first position, the second position, third, fourth, fifth, sixth, seventh and eighth. And then let us do this in case of the benzene molecule. Basically what we are now going to do over here is we are encoding everything in terms of the C's and the 1's. Now in the first position I have a C, in the second position it's about the ring closure, so I don't have anything in here. Third, fourth, fifth, sixth, seventh position I have got C's, and therefore I put 1 for all of them, and again in the last position I am actually closing the ring, so there is no C. Similarly, when I am talking about the 1's, the rings opening and closure, in the first I have a C, and then after that I am actually opening the ring, so I put a 1. After that I am not really opening or closing any of the rings until I get to the last position, and then here once again I put a 1. So as you can see, by using a combination of small c's and 1's, this benzene molecule can actually be encoded to give us a feature vector that looks like this. Alright. So this is how one can do molecular representation using the SMILES system. Now SMILES is very convenient. It is one of the earliest representation forms, but then there are some disadvantages with SMILES as well. So primarily the main disadvantage is it's just a string based systems, and you really do not have any way in which you can check whether the molecule being written out is actually a valid molecule or an invalid molecule. So this is one challenge. So one could, for example, simply write C1 C C C C. So okay, I have got now 1, 2, 3, 4, 5 C's. So that means it would be something like this. But then I am starting the ring and I am not really closing it. So that cannot be something which is physically correct, and therefore a representation like this, even though SMILES system is going to allow it, this type of representation is actually going to be an invalid representation. And so something like this is really a key challenge with the SMILES type of system. Now this means that we need to come up with some sort of much improved representation scheme which goes beyond the SMILES. So for that, people extended the SMILES type of nomenclature, and then they came up with something called deep smiles. We are not really going to discuss the deep smiles, because even though it has some advantage over smiles, it still contains some of the problems of smiles as well. For example, even with deep smiles, we don't have a way of checking whether a molecular entry is actually a valid entry or an invalid entry. And so that's why we move on to the next system, which is known as selfies. So selfies, like smiles, is also acronym. It stands for self-referencing embedded strings. And selfies is also a text-based notation, but it can now start encoding the bonds, it can now start encoding the branching. And this is the major advantage. And instead of using just the letters, we use something like a token in case of the selfie system. So here, ethanol is encoded using 3 different tokens. So what do I really mean by it? These tokens have some meaning. For instance, if I write just C like this, a capital C, then like carbon, I am actually talking about a non-aromatic compound. But then since nothing else is specified, I am going to make an assumption that this thing is essentially going to be a single bond. So if I simply use CC, it means that there is going to be a carbon-carbon single bond. So when I am talking about ethanol, essentially the molecule is going to look like this, and what you see is between the first carbon and the second carbon, I've got a single bond. And then after that, we have this hydroxyl group, which is also connected to this carbon by a single bond, and therefore we simply use it as C, C, and O. Now, anytime you've got a double bond, you have to put the symbol for the double bond in front of the letter. So for instance, a double bond would be depicted like this, and so if I write something like this, then what that means is I have got 2 carbons. In front of my second carbon, I have this double bond. So what this also means is now I can basically attach only a couple of hydrogens over here. And here, what you will notice that the nomenclature that I have written was something like this. There is nothing after this carbon, and therefore one has to assume that you have got the hydrogen atoms over here as well. And so you have a molecule like ethylene being represented in this form using selfies. So this is one advantage that selfies have, because you start encoding the information of the bond. Now that also brings in some issues with selfies. It also means that the notation now starts becoming a little bit more cumbersome than smiles, and therefore a lot of people still go ahead and include smiles, of course with the caveat that they have to be very, very careful in order to not bring in any of this invalid molecular entry. As long as you are working with valid molecular entries, that's fine, but then that also requires a little bit of domain knowledge on part of the user who is actually going to use this type of machine learning programs with this kind of representation. Now, there are many different ways in which one could fingerprint an organic molecule. So key among them would be structural key fingerprints. These are very common. Then you've got topological fingerprints, which looks at the molecular topology. Essentially, what this does is it is simply looking at the path or the chains, the path on the chain by which different carbon atoms are connected. So topological fingerprints are yet another type of fairly common fingerprints. And then you have got circular fingerprints. And beyond that, nowadays, there are lots of advanced representation. So things like pharmacore fingerprints, hashed and hybrid fingerprints. Hashed and hybrid fingerprints, this we'll talk about very, very briefly when we discuss the topological fingerprints going forward. And then you have got 3D fingerprints, which is actually going to capture the 3D structure of a molecule. Now, out of all of this, we are going to discuss the first 3 in a little bit more detail. So in case of structural fingerprints, your molecule is encoded as the presence and absence of different predefined structural fragments. When you are talking of topological fingerprints, what we are really discussing over here is we are looking at path-based fingerprinting, where you have got a way of encoding a sequence of bonds or atoms or paths up to a given length of a chain. So essentially what they're doing is they're recording the atoms and bonds on a graph. So again, when you are using topological fingerprints, you are kind of bringing in the concepts of the graphs that we had already discussed in one of the previous lectures. And when you are defining the path, by convention, we stick to 2 to 7 uh, positions in that path. You could, of course, go for longer paths as well. But then you have to draw a limit somewhere, because the longer the path lengths that you are considering along the carbon chains, the more complicated the description starts becoming. So that is why people usually consider somewhere between 2 to 7 carbon atoms for a given path. And then finally, you have got circular fingerprints. So in case of circular fingerprints, these basically encode the local environment of the atom, their atom-centered descriptions. And essentially what you are doing is you will specify a radius, and then you are going to look at the atoms and how they are arranged around the reference atom in your molecule. So in that sense, this kind of brings in this idea of nearest neighbors. Of course, when you are talking of nearest neighbors for this organic molecules, you are basically looking at a circular neighborhood. Now, let us talk about this individual fingerprints, and we'll start with the structural key fingerprints. So when you talk about structural key fingerprints, these are actually fairly simple-minded way of encoding the molecular information. And when you talk about the structures, the simplest substructures are going to be the elements themselves. So you can put carbon, nitrogen, oxygen, sulfur, whatever you want as a structural unit. Now, these elements may well be the simplest substructure, but when you have large molecules, using elements as the substructure is not very practical, because that will result in a very messy description of the molecule. And therefore, what we do, instead of using the elements as substructure, we start using things like the functional groups as different substructures. And so it's really the presence or absence of functional groups which are getting encoded in this type of fingerprinting process. Now, you will find that you've got tools like the Max keys or PubChem, which are actually inbuilt in a number of cheminformatics packages, and they can use, among other things, the structural key fingerprints as well. Now, there can be other types of substructures that can be encoded. So things like bonds or aromatic rings, those can also be encoded. And depending on how long the descriptions are, you will need different amount of bits in order to represent these types of molecular structure. So Max keys are set up so that these are 166-bit representation. So this 166-bit representation is fine for a lot of the molecules, but if you really want to look at the much longer molecules, then you want to go with this PubChem type of formalism, which are about 881 bits. Now, there are other categories of representation and structural fingerprints descriptions as well. So you have got this atomic environment type, you have got a SMARTS pattern. So SMARTS stands for Smiley's Arbitrary Target Specification. This is something which is very well integrated with SMILES. So SMILES basically describes a molecule, and then the SMARTS is going to describe what type of patterns that number of molecules will match. So in that sense, using the SMARTS pattern is a very good way of searching whether a sequence of certain structural units are present in an organic molecule or not. So let us look at the structural key fingerprints with an example, and we'll take the example of epoxy resin, and then we will become a little bit more specific by saying that we are looking at DGEBA. It's a type of epoxy. It stands for diglycidyl ether of bisphenol A. So let's quickly write the structure for this. So I've got a CH2, CH, CH2, and then I've got oxygen bonded over here, another oxygen, and then I have this aromatic ring, a carbon which has got two methyl groups added to it, and then this molecule is basically getting repeated or mirrored, I should say. So the rest of the structure will therefore look something like this, and I have to add the oxygen over here. Okay. So in order to encode this information carefully, I will need to start defining some structural keys. And to keep things simple, I am going to work with 14 keys. Now there are other substructures that can be added as structural keys here, but let me get into a situation that I am creating my feature vector with only using 14 different keys. And frankly, for this specific molecule, we do not need any of the other keys. So how do I actually represent this? I will have to write the key number, and then I have to write the value corresponding to the key. Remember, we are basically creating some sort of a feature vector type of representation. So I have got 14 keys. So let me start writing them down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then finally 14. So the first key talks about whether an aromatic ring is present or not. And we say that yes, the aromatic ring is present. The second key talks about whether a benzene ring is present or not, and yes, a benzene ring is actually present over here. Now how about the third key? It is talking about whether we have got an aliphatic chain, and yes, the aliphatic chain is present. It talks about whether we have got ether type of linkages. Fifth one is about epoxy type of linkages. All of them are present. We do not have a hydroxyl group, so the value for this key becomes 0. We do not have carbonyl, so the value for this key becomes 0. We are not having any halogens over here. We are not having any amines over here. Do we have some sort of branching? Yes, we do have branching, so I'm going to put the value here as 1. We do not really have any ortho substitution, para substitution, so on and so forth. Okay, and then similarly you can put the values for the methyl group, ethyl group, and that's how you can actually create a structural fingerprint for a reasonably involved molecule like a epoxy.